Hello everybody, and thanks for coming. My name is Cervan Constantinescu, and today I'll be presenting you the process that we went through for bootstrapping ARM64 support in Android. So just a quick overview of my presentation. I'll be talking in the first part about Android on 64-bit kernels. So I'll be touching here compat layer, so that's support for 32-bit Android user space on 64-bit kernels, as well as 64-bit ABI. And in the second part, I'll be talking about 64-bit Android user space, and here I'll be talking about Bionic, Binder, as well as nandroid. So just a quick slide about myself. I'm a software engineer working at ARM. I've been commenting the ARM Versatile Express Android ports. I've been working on Binder, HMEM, as well as Bionic. And currently I'm working on ART. So I guess most of you here are familiar with this slide, and probably you saw all the namings here and you already know what I mean. But I think it's useful just to have a quick overview about what ARMv8 means and what AR32 and AR64 mean in the ARM context. So ARMv8 is the 64-bit ARM architecture. It has two execution states, 32-bit execution state, AR32, and a 64-bit execution state, AR64. The 32-bit execution state, it's a superset of ARMv7. It can execute two instruction sets, that's A32, previously known as ARM in ARMv7, and T32, previously known as STAMP in ARMv7. AR64, so the new execution state, the 64-bit execution state, executes the A64 ISA. And I'll be talking in the second part of my presentation where I'm talking about the user space support. I'll be talking mostly about the A64 ISA. ARM64, it's the name for the 64-bit ARMv8 support in AOSP as well as the Linux kernel. So you will see the ARM64 naming referring actually to the AR64 execution state of ARMv8. So in the first part, I'll be talking about Android on 64-bit kernels. So in May 2012, we have been given the objective to boot Android ice cream sandwich on ARMv8. At this point, we already had Android working on our Versatile Express ports. That was ARMv7 Android ICS. And our goal was to implement this with no user space changes. So all the changes will be implemented in the kernel. And we had a kernel which was running in the AR64 execution state, early 3.3 Linux kernel with early support, early AR64 support. So we had the Linux kernel at this point. As I mentioned, it was a 3.3 Linux kernel. The support for ARM64 was upstream in the Linux kernel a bit later. And at this point, it was booting Linux. And you can see that I highlight here booting Linux. It's probably the first step that you have to do when you port Android to a new platform. You need to make sure that your platform boots Linux. There's no point of carrying on if it doesn't boot. So it was booting AR64 open embedded file system, so that's 64-bit Linux file system, as well as 32-bit Debian port for ARM. And I'm mentioning that 32-bit Debian port because I want to emphasize that the compat layer for Linux was already working at this point. However, for Android, we needed two more subsystems. That's HMEM and Binder. And here I'm talking about Android with a minimal set of hardware support, so no hardware graphics, no ION, or other such systems. So let's take a look at what HMEM and Binder do for Android. HMEM is the shared memory allocator used by Android. It's similar to POSIX SHM. And actually some of its functionality is implemented on top of POSIX SHM, but has some special properties. It has the ability to have named memory spaces, as well as it can discard memory when under memory pressure. And this is the type of memory allocations that we use for the Dalvik or the ART heap. Binder is the IPC mechanism used in Android. It is basically used whenever you communicate with other processes inside Android, or when you try to draw to the screen. And I've been struggling to find a good one-line description of Android and of Binder. And I think the best one is this one by Diane Heckborn on LKML. And I'll be quoting her. In the Android platform, the binder is used in nearly everything that happens across processes in the core platform. Both of these drivers currently live in the staging area in the Linux kernel, and you can go and take a look. So the problems that we faced with the kernel can be split into two categories. And the first one is the IOP tool interface. Probably not the wisest chosen font, but anyhow, I hope you all see this. So as you can see, the normal way of doing an IOP tool is opening a device, in this case, HMEM, then doing a specific IOP tool, in this case, HMEM set size, and then jumping in the kernel and executing the specified command. But as you can see, when we started with doing this, instead of returning 0, we were returning ENOTDR. And again, this is a really simplified view of HMEM. So what was happening? You can see here that we use size passed to the IOP tool. So actually the size is a size T. But size T differs in a 32-bit execution state compared to a 64-bit execution state. So in this case, HMEM set size, which is the command passed to the IOP tool, is a union of HMEM, which is a specific magic number, 3, which is the type of command. For example, get size is 4, and the type, which is passed between the kernel and the user space. So the correct fix here is to have a thin compat layer that expands the commands to the ones that you actually are meant to use. So the other problem was with the ABI. And here I chose Binder. I'll be talking a bit more about the changes that we did to the Binder interface next month at Linux Flowers. But as you can see, the structure doesn't actually mirror what's supposed to be used for. We want 8 bytes, but we specify unsigned long types and flags, and then we have a signed long handle, where we know that handles most of the times are unsigned types. So this mirrors other changes that we did to other subsystems, but it's a good example. So we went ahead and specified the type, the size, and the types that we need in the interface. And this is the interface that's used by the kernel and the user space. So it's the user API interface. You can see that we also added the user definition around user space pointers, which actually helps us in the kernel side identify which type of pointer it is. And if it is a user space pointer, then we need to add some special handling. And most of these changes replicate throughout the 32-bit compact layer. So shortly after, in August 2012, we demoed one of our internal conferences, 32-bit RV7 user space working on a 64-bit AR64 kernel. And following this, we posted the first set of patches to LKML. As far as I am aware, these are the first patches that support 32-bit Android user space on top of a 64-bit kernel. So what were my takeaways from doing this work? You should use explicit size types in your UAPI structures. We should use, whenever possible, use native kernel types. So, for example, PIDT or KT, and so on. You should use all the kernel compat types. So in the previous slide, I talked about size T and size T differing in a 32-bit user space and a 64-bit user space. The proper fix in that case is to use compat size T inside the kernel. Try to use the kernel expansion, the compat expansion macros. So you get a 32-bit pointer, you need to expand that to fit it in a 64-bit type inside the kernel. Ensure the alignment of individual structures. And as you might know, compilers tend to add so-called dead memory spaces so that they ensure a proper alignment of your structures. Where you don't want that, you can easily specify the alignment with toolchain directive. And provide a thin compat layer for your 32-bit user space. And if you click that link on my PDF version of the slides, it will take you to what I think is a really good example of the compat layer. It's what we implemented in Azure. So in the second part, as I mentioned, I'll be talking about 64-bit user space, support in Android. So in September 2012, we set ourselves the task of bootstrapping the ARM64 Android port. At this point, Android was only compiling for 32-bit architectures, and this is AOSP as of October 2012. So we needed to add support for ARM64 as well as the LP64 programming model. And we wanted to enable development for a 64-bit VM. And probably most of you guys attended Monday's talk where Stuart described what we did for porting Alvik and further on art. And we wanted to ensure communication between 64-bit processes as well as 32 and 64-bit processes. So probably most of you are familiar with this slide again, but I think it's really useful for what's about to follow and what I'll discuss in the following slides. So the ARM64 procedure calling standard, it's different from the 32-bit one. And as you can see, for 64-bit ARM, we have two register banks, the general purpose register bank, where we have 31 general purpose registers, and the floating point register bank, where you have 32 vector floating point registers. So there are two views of every register in the general purpose bank. There's an X view, where we view the register as a 64-bit entity, and there's a W view, where we view the register as the lower 32-bit of X register. Similar from the floating point side, there are three views. One is the Q view, where we view the register as a quad 128-bit. Then we can view it as the lower 64-bit part of a Q register. So that's the D register used for double floating point values. And there's the S view for single precision floating point values. And as you can see, we always have the floating point unit compared to ARM32. So we always pass vector floating point values in the V registers. So we use R0 to R7 and V0 to V7 for passing arguments. And the other registers according to the slide here. So Bionic. Bionic is probably one of the first projects we touched in the Android user space. It's Android's libc, libm, and linker implementation. It's a derivation of BSD. BSD is a standard C library, and it's almost POSIX compliant. And a good example here is the thread local storage mechanism, where POSIX mandates that we need to have 128 slots. And we have, in Android, we only have 64, and actually some of them are used for some special handling local to Android. It has a custom linking mechanism that I'll discuss in the following slides. And at this point, once again, it had no 64-bit support. So one of the most important interfaces exposed in libc, it's the syscall interface. It's basically the interaction between the kernel and the user space. And I'll take some time here and talk about the ARM64 implementation of the syscall set. So ARM64 implements what's called the canonical syscall set. It's a modern restricted syscall set that implements the syscall add family. And for those of you not familiar, a simple example is open and open-add, where for open you have the relative path, and for open-add you have the absolute path that you want to open the file at. So therefore, open-add is a superset of open, and open can be implemented using open-add. So older architectures used to implement both variants. Newer architectures implement just the superset, in this case open-add. Arguments are passed in x0 to x7, and probably you can see here that I mentioned no D registers, no floating point values. That's because there's no syscall taking floating point values. Therefore, all the arguments passed to syscalls will live in integer registers. And the syscall number is passed in x8. If you want to take a look over the implementation and the syscall's numbers, you'll find it inside the unistandard.h in ASM generic inside the Linux kernel. Bionic syscalls, the Bionic syscalls are described in syscall.txt. They are, in most cases, automatically generated using a Python script that I described there. And there are special cases for fork, clone, and so on, where we have a customized wrapper against the syscall. So another important part of Bionic are the optimized string routines. And here I would like to thank Linaro for their work in implementing these string routines and upstreaming them to ASP for the ARM64 port. So I would like to take some time here and discuss about the generic implementation. This is what we use for ARM64 compared to ARM32. So for ARM32, we have memcopy variants for Cortex-A15 or Cortex-A9 and so on. For the ARM64 port, we very much encourage using a generic string routine optimization. So this is something that should perform well across ARMv8 CPU implementations. And ideally, we wouldn't want to see any CPU variant specific optimizations like we do for ARMv7. As you can see, there's a short comparison between AR32 and AR64. I hope you can make the distinctions between the colors. So all the benchmarks quoted here are part of the Bionic benchmarks, and these slides are also available online, so you can probably take a look in more detail there. But the general trend is for ARM64 to be performing better than ARM32. Again, higher is better performance. The other important part of Bionic is the libm implementation. I would want to take some time here and just emphasize the fact that ARM64 is always hard float. There's no such thing as soft float for ARM64. We always pass floating point values in D or S registers. Another important change that comes with 64-bit ARMv8 is the splitting of what previously used to be the control and status register in two registers, one used for control and the other one used for status of the floating point unit. And this makes a big difference in modern out-of-order CPUs. And again, you can see that the general trend for AR64 is to be faster than the 32-bit implementation. As I mentioned in my first slide, Android provides its own linker implementation. So that's different from the one that you would have in a normal Linux distribution, where you have lib.le.so doing the linking for you. In this case, we have system bin linker, and that's for existing 32-bit applications where the ELF files have already specified their interpreter field as pointing to system bin linker. For new 64-bit ELF files, we point them to system bin linker 64 for doing the linking of the shared libraries. And similar, we have a multi-lib environment for the libraries. So we have two paths, one for the 32-bit libraries, that being system lib and vendor lib, and a similar one for 64-bit system lib 64 and vendor lib 64. So Bionic also provides a set of benchmarks and tests. You have a 32-bit variant and a 64-bit variant of both the tests and the benchmarks. It's slowly developing. We have many more tests than what we started with, and many of them have been introduced with a 64-bit port, either by us, either by Google. And I would like to emphasize that you should definitely make sure that you run both the 32-bit and the 64-bit tests, as well as the benchmarks before submitting patches to AOSP. As well as I would like to encourage you to extend these tests and benchmarks as much as possible. So just a quick statistic for ARM54, the Bionic port. So we have around 120 commits in our internal code base. That's before merging and cleaning the patches for upstream to AOSP. There are about 10,000 lines, including automatically generated files. And you can see that the general trend is for 64-bit to be faster than 32-bit. And a good example is the geometric mean of the results, which is the last column on this slide, where you can see that AR64 outperforms AR32 on the same CPU. So we ported 64-bit. We have a 64-bit libc, we have a 64-bit libm and a linker, but we have no communication between 32-bit and 64-bit processes. And this is what Binder is used for. You can see here in this slide that we have two processes, a 32-bit process and a 64-bit process. And the data is being passed basically from the 32-bit process to the 64-bit one through the kernel driver of the Binder. And you can spot here that the important thing is to be able to have the same protocol for both processes. So the Binder protocol, the one that lives in the user space, just beneath the user data, it's the one that's really important here. We need to ensure that this protocol is understood by both views of the world. So the Binder protocol is abstracted away in Service Manager and libbinder. Service Manager is the governor for the Binder interface. And again, I'll be talking a bit more about Binder next month at Linux Plumbers. So the idea here is that we want types as void star and size t to have the same size for both worlds, and the common denominator here is the 64-bit size. So we redefine void stars and size t's to uint pointer and size t, and we type those to 64-bit or 32-bit, depending on the switch of the protocol. So the switch is actually used, its target uses 64-bit binder. Setting this to yes would mean that you use the 64-bit protocol. So you use the 64-bit protocol for 32-bit and 64-bit processes. So that's 64-bit supporting the user space, as well as for 32-bit user space running on top of a 64-bit kernel, where all the compat layer that I talked about previously is done in the user space. So I mentioned in one of the slides that our aim here was to boot to shell. And for that, we use what we internally call nandroid. So nandroid is an Android environment that boots to shell and stops there, doesn't bring up the UI and all the other complicated frameworks. It's basically a modified init-rc that only starts the required services. So all the other ones are set to disabled, which in the Android init-rc world means don't start this service. We give special privileges to the root, to the shell, and it has been really useful for us for developing. We even use it now when we have the whole system booting to GUI. We use it for developing art or any other systems that don't need the full-blown Android. It can speed up build times, and I guess most of us here that build Android know that it takes a while to build Android. So having a shorter list of dependencies automatically speeds up your build time. So you can see here an example of a nandroid or nandroid in ithRC, where we set special privileges to the shell and also disable some of the other services. So in January 2013, we got to the stage where we were putting 64-bit nandroid on top of a 64-bit kernel. And so as you can see here, the user space is 64-bit, so you have a generic ARM64 shell that prints what the kernel reports as an architecture, in this case, ARM64, so 64-bit kernel. Thanks. Any questions? Questions?
You stopped in the middle. It was January 2013.
Yes. So what happened from here onwards? Yes, we started, so I think from here onwards, okay, so this is a year later. From here onwards, we started working on Dalvik and all the other frameworks. And I think November 2013, we started upstreaming patches. Probably we had a full-blown boot to GUI I would say mid 2013, though I might be mistaken.
So is there a clear write-up to know how to build this nandroid?
How you can build nandroid? So I think the simplest thing to start off with is to build the whole Android and then to modify the initRC as I specify here in these slides. And then the idea is that you need to find the highest dependency in your build system. So in this case, the highest dependency was the Android shell, and specifying make Android shell would build libc, linker, libm, and all the other systems that you need behind this. It depends. You might need the shell and service manager or some other service, and then it changes. You have another highest build dependency. Any other questions? I guess the ARM guys already saw the slides a couple of times by now, so they probably asked me all the questions by now.
So, was it all straightforward, or did you have some nasty, sneaky things going wrong behind the curtains you had to spend lots of time finding?
So, could you repeat the questions? What were the interesting things?
So you've shown us what you did and what you had to change and all of those things. Were they all straightforward things, you just had to implement it, or did you have some crazy stuff that was going wrong and you had to spend lots of time figuring out?
Yeah, I think we had to spend lots of time figuring out things. We were the first, so to our knowledge, we were the first 64-bit architecture, at least in our code base. So there were lots of assumptions that were wrong. We had really difficult to fix patches, bugs. Probably one of the most interesting ones was in set jump, long jump. I managed somehow not to save one of the registers, so saving 24, 26, but not 25. Actually, fortunately for me, I was on holiday, so I didn't have to fix this bug which I introduced. But Dave and Stuart spent lots of time debugging this. So there were lots of things which were challenging and tricky. And probably you can see the simplest thing to follow the patches would be to look at the commits. Service Manager is probably a complete rewrite. It's a really complicated system on top of Binder. It's much cleaner now and much easier to use. So yes, there were lots of complicated things.
Compatibility.
Yeah.
So 32-bit compatibility. So we didn't start off with the assumption that we'd have 32-bit compatibility, did we?
Yes. So we started off with having a full 64-bit Android user space. So no 32-bit commands were working. there was no system bin linker 64. There was a system bin linker that was a 64-bit linker. So once we managed to get all this to the finish line, we went back and looked at how we can support 32-bit applications working together with 64-bit ones. So this is probably a simplified view, but 64-bit communication to 32-bit processes wasn't on the initial priority list. Any other questions? Okay, thanks for coming. I hope it was useful. Thanks.